the previous session we studied CNNs. We also learnt how to build CNN models with transfer learning. In this session we will build image classification models from scratch, and we will use bunch of strategies that are employed in practice while building image classification model, and we will also visualize what the CNN is learning by looking at the activations after each layer. So, we will follow a basic machine learning workflow. We will examine and understood where we will examine and understand the data. We will build the input pipeline to bring the data to the training. We will build a model, then train it, test it, and then we will improve the performance of the model and repeat the process. We will get some practical experience and develop intuitions for building input pipelines for images using image data generator class. We will also study how to identify overfitting and prevent it, and we will also learn key concepts like data augmentation and dropout in this exercise, in this session. Let us install TensorFlow 2.0. Let us import image data generator and other libraries like dense, convolution 2D, flatten, dropout and max pooling 2D from Keras layers, and we will also import sequential for building model. We use matplotlib.pyplot for plotting the performance of the model. Let us load the data. We use dogs versus cat dataset from Kaggle competition. The dataset has the following structure. There is a top level directory called cats and dogs filtered. Then we have training and validation dataset. Within training dataset there are two subdirectories, cats and dogs. The validation directory structure also follows the same. The validation also has two subdirectories, cats and dogs. Within cats directory we have images of the cats stored in JPEG format, and each file has a name cat.id.jpg and dog.id.jpg. So, first 2000 examples are used as training and the remaining examples are used for validation. After extracting the content, we assign variables with proper file paths for training and validation sets over here. Then we construct paths for training and validation directories for cats and dogs. Let us look at how many cats and dog images are there in training and validation directory. We use os.list directory command to list the content of the directory and take the length of this directory listing to calculate the number of cats and dogs in training and validation. You can see that we are using 2000 images for training and 1000 images total for validation. 1000 cat images are used for training and 500 cat images are used for validation. The same proportion of images are used for training and validation from dog class. So, let us set up some variables like batch size, epoch and the height and width of the image. Let us let us prepare the data for training. So, we perform the following steps. We will first read the images from the disk, then we will decode the content of these images and convert them into proper grid format as per their RGB content. Then we convert them into floating point tensors, and then we rescale these tensors from values between 0 and 255 to values between 0 and 1. So, all these tasks are done by image data generator class provided by tf.keras. It can read images from the disk and preprocess them into proper tensors. It will also set up generators that convert these images into batches of tensors, which is very helpful during the training. So, we set up image data generator for training and validation set. After defining these generators, we use flow from directory method to load images from the disk, apply rescaling and resizing of the image into required dimension. So, here the target image size is 150 by 150 and we want to shuffle the training data. We do not shuffle the data in the validation set. We also specify the batch size and the directories where data is stored. Let us visualize the training images by extracting a batch of images from the image generator. Let us plot 5 of these images. We use matplotlib for plotting these images. So, these are some of the images of cats and dogs. Let us create a model, a CNN model for classifying cats and dogs. So, we use 3 convolution blocks with a max pool layer in each one of them. Then we use a fully connected layer with 512 units on top of that with ReLU activation, and the model outputs class probabilities based on binary classification by sigmoid activation function in the output layer. Let us look at the structure of the model. So, we use a convolution 2D followed by max pooling, then another convolution layer, we use 16 filters here, 32 filters here and 64 filters over here. We will use binary cross entropy as a loss with Adam as an optimizer and accuracy as a matrix and accuracy as a metric to track. Okay. So, it will be an interesting exercise for you to understand the output shape of the model and work out the model parameters as you see in the summary. So, I would encourage you to stop a video for a couple of minutes and work out these parameters for yourself as we have done as we have done in some of the previous sessions. So, you can see that we have a model with more than 10 million parameters. Let us train the model for 15 epochs. Okay, so after 15th iteration we got accuracy close to 94% on the training set and 73% on the validation set. Let us visualize the training and validation accuracy across epochs. You can see that as we trained for more epochs, the training accuracy kept rising, whereas the validation accuracy plateaued after some time. We also see the same trend in the training. We also see similar trend in the training and validation loss, where we found that training loss was consistently decreasing as we train for more epochs, but validation loss initially declined, but then rose steadily after certain epochs, after about 5th epoch. So, this points to the fact that the model is overfitting. So, we have to explore strategies to increase the performance of the model by reducing the overfitting. So, we will use data augmentation and dropout as two strategies for fighting overfitting problem. In data augmentation, what we will do is we will take the existing images and perform certain transformations on them to gather more data. So, what kind of transformations we do? We can rotate the image, we can translate it, we can change the scale of the image to create more and more examples of the image. The model is less likely to overfit with more data. So, let us try to augment the data and visualize it. We can perform a random horizontal flip augmentation to the data set. So, we can use image data generator with horizontal flip equal to true, and let us generate the data. Let us take one example and see how the data got augmented with horizontal flipping. So, you can see that after horizontal flipping we get different, after horizontal flipping we got more examples that were generated from a single example. We can also do a different kind of augmentation by rotation. Let us apply 45-degree rotation randomly to the training examples. Now, you can see that the same picture of the cat was rotated in different orientations with different angles, and by applying this particular data augmentation strategy we created more pictures from a single picture. In addition to that, we can also apply zoom augmentation by specifying the zoom range. Let us see how zoom augmentation look like. Let us put together all these augmentation strategies. So, we tried horizontal flipping, we tried rotation, and we tried zooming, and we will use all these augmentation strategies together to get more images from the set of training examples. So, we use image data generator and apply rescaling, then rotation of 45 degrees, then wide shift, height shift and horizontal flip, and the zoom augmentation to the training images. Okay, so what we do is we apply all these augmentation techniques to the training set and obtain more data by augmenting the original images. So, these are some of the augmented pictures of a dog, where we have an original picture over here, and these are the pictures that were obtained by applying various data augmentation strategies. We apply the data augmentation only to the training examples. We do not apply data augmentation on the validation examples except rescaling them. And we also convert the validation examples into batches using image data generator. Another technique to reduce overfitting is dropout. We add dropout to the model after augmenting the data through various augmentation schemes. We add a dropout of 0.3 each after couple of max pooling layers and dropout of 0.1 after the fully connected layer. The effect of the dropout is that the randomly 30% of max pooling nodes and 10% of fully connected nodes are set to 0 during each epoch. We compile the model and train it, and we can see that at the end of 15th epoch we have a training accuracy of 64% and validation accuracy of 63%. And if we plot the losses, you can see that both the training and validation loss is trending together, and there is a lesser overfitting than the earlier model. Let us visualize what this particular CNN is learning. So, what we will do is we will take the output of the model after every layer. So, there are 8 different layers: convolution followed by pooling, then there is a dropout, then convolution, pooling and dropout. So, what we do is we get the output after every layer. So, this is different from the models that we have seen so far. This is the first time we are encountering a multi output model. Until now we have models that were giving exactly one output at the end of the final layer. Here we are gathering output after every layer. Let us look at the predictions coming from the activation model, and let us plot those activations. So, this is the input, this is the first image that is input to us, and the first level activation is essentially 150 by 150 feature map with 16 channels. So, let us look at the third channel. You can see that the third channel is roughly detecting the edges from the cat picture. If you look at the 15th channel, it is identifying probably the overall shape of the image. At this point, let us go and plot a complete visualization of all the activations in the network. We will extract and plot every channel in each of our 8 activation maps, and we will stack the results in one big image tensor with channels stacked side by side. So, now you can see that the first convolution layer seems to be detecting edges, and as we go deeper and deeper in the network, we are detecting different kind of features from the images. We can see that there are a lot of empty spots after the second convolution and max pooling operation. There are few remarkable things to note here. The first layer acts as a collection of various edge detectors. At that stage, the activations are still returning almost all the information present in the initial picture. You can see that a lot of features from the input are being preserved. As we go higher up, the activations become increasingly abstract and less visually interpretable. They start encoding higher level concepts such as cat ear and cat eye. Higher up representations carry increasingly less information about the visual content of the image and increasingly more information related to the class of the image. The sparsity of activations is increasing with the depth of the layer. The first layer, almost all filters are activated by the input image, but as we go deeper and deeper in the network, there are more and more blank filters. This means that the patterns encoded by the filter is not found in the input image. So, this is a very nice way of visualizing how convolutional neural network is learning patterns in the image. So, we showed a very important universal characteristics of representations learned by deep neural network. The features extracted by a layer get increasingly abstract with depth of the layer. The activations of layers higher up carry less and less information about specific input being seen, but more and more information about the target class. A deep neural network effectively acts as an information distillation pipeline with raw data going in and getting repeatedly transformed into and getting repetitively transformed so that irrelevant information gets filtered out and useful information gets magnified and refined. Hope you had fun learning these concepts. See you in the next class.